Hello everyone, this is a quick review of thermal. We'll look at the thermodynamic cycles and what are called closed systems and open systems. Then we'll provide an overview of what differentiates the two primary classes of thermodynamic cycles, which are power cycles and pump cycles. We'll then more specifically focus on the heat pump cycle and the famous coefficient of performance COP before describing what we intend to do in this lab today. So what is the definition of a thermodynamic cycle? A thermodynamic cycle, as you surely guessed, is a series of processes which return to the system to its initial state. So it's like a loop. You start in one state, go through some processes and come back to the exact same point. So there are two main families, the closed cycles and the open cycles. So what are the closed cycles? That type of system can exchange only energy with its surroundings, but it cannot exchange matter. So as an example, if we put a tightly fitting lid on a pot of water on the stove, it would approximate a closed system. Earth as well can be considered as a closed system since it only receives sunlight, energy, while the overall mass of the Earth stays constant without any exchange with space, from space. Now, that was the closed system. And now, what is an open system? And the difference of the other one is open system can exchange both energy and matter with its surroundings. So, to give an example for this one, if you're this time eating the same pot of water on the stove without lid, the system will include the stove, the pot, water, while the surroundings, and it's open, would be everything else, the rest, for the kitchen, the house, neighborhood, etc. That's an open system. So humans also, like all living things, are open system, meaning that we exchange both matter and energy with our environment. In all cases, the thermodynamic cycles, all of them, involve the movement of heat and work in and out, work in, work out. So here's a closed cycle example. It's like you have here a pot containing gas with a perfectly tight lid. It's like a piston. So the cycle begins with a gas which is confined in a cylinder. The volume of the cylinder is changed by a moving blue piston here that you see, and the pressure is changed by placing or removing those green weights on the piston. So we have two sources of fire, two sources of heat. You have the fire, and you have ice as well, which is another source of heat, but it's colder. So initially we are in the first state, like here, P1, V1, T1, at high temperature, high pressure. You can see it's the highest pressure we have here, and low volume. Here, this is lower volume. So the first process performed on the gas is an isothermal expansion. So when you go to P1, V1, T1 here, to this state, you see we are following the isothermal line. Its curve is the same temperature. So the fire heats the cylinder, and the weight is removed here. Should have shown that removed, which lowers the pressure in the gas. But anyway, the temperature remains constant, but the volume increases, as you see. And during the process from here, P1, V1, T1 to P2, V2, T2, T1 here, heat is transferred from the source here, the fire, to the gas, and we maintain the temperature. We will note that the heat transfer is here by Qn. We will note the heat transfer by Qn into the gas, so that comes from the fire under the cylinder. The second process performed on the gas is an adiabatic expansion. It goes from here to here. It's like going from here to here. So during this process, no heat is transferred to the gas. No heat is transferred here. That's the definition of adiabatic. Then the third process to the third process P3, V3, T2 to this one here, you see that it's performed, from P3, V3, T2 to P4, V4, T2 here. It's performed the gas in a isothermal compression. Here, same thing, we are like following that isotherm, same temperature between here and here, between here and here. The ice is brought into contact, as you see, with the cylinder. We remove some weight, which raises the pressure in the gas. Okay. Weight is added normally. We add some weight, which raises the pressure in the gas. The temperature remains constant, but the volume decreases, as you see. The volume decreases. During this process, heat is, even here, is still transferred from the gas to the heat source to maintain the temperature. Okay, from the gas to the heat source. We will note here that the heat transfer by Q out, away from the gas. So from, as you certainly remember from the first law of thermodynamics, here is a weight added. The amount of work produced by this cycle is Qn minus Q out. That's again that is the area of the cycle inside here. That is the ideal cycle. Ideal. It's called the Carnot cycle, and it's actually a reference. We'll never be able to reach this. There are all sorts of deviations from adiabatic or the isotherm. It's never exactly, but it provides again a reference and the upper limit of the efficiency during the conversion of heat to work. So that Carnot cycle is what we have here. And it is also, you would see, Carnot cycle applicable to the efficiency of the refrigeration system, and we'll look at that in a minute. It's again not an actual thermodynamic cycle, but it's a theoretical construct. Yeah. So this is, as I said, an open system can exchange both energy and matter with its surroundings. So the stovetop example would be an open system because heat and water can be lost in the air if you leave the lid open. And a gas turbine, represented here, is an internal combustion engine that operates with rotary rather than reciprocating movements or motion. As a matter of fact, I think the next lab will be about the gas turbine. So gas turbine are composed of three main components. You've got the compressor here. You've got the combustion chamber, and the power turbine here. In the compressor section, you've got air drawn in, air intake here, and it's compressed generally, varies, but about 30 times from the atmospheric pressure, so it's a very good ratio. And it's directed then to the combustion chamber, where the fuel is introduced, jet fuel, kerosene, and ignited burnt. Then it goes to the turbine here, and so you see the turbine there is a shaft between the turbine and the compressor. So when the work is produced here, it also produces internal work to move the compressor. So yeah, they are connected by a shaft. So here the fuel is burnt at essentially constant pressure, as you see. It's called isobaric. So constant pressure here. And the heat rejected from the turbine is also at constant pressure. So this is called the Brayton cycle, and it's an idealistic cycle as well, but the same thing, we want to get as close as possible. The engineers are trying to reach something that would be as close as the ideal Brayton cycle. So as you see, there is, again, to recap, here you got the compression, a diabatic process, and it's the same as isentropic because it's reversible. Then you go to the heat addition, the combustion chamber, isobaric, same pressure. Then you go to the another adiabatic process during the expansion, and another, again, isobaric process here for the heat rejection. So so that's what we have, so thermodynamic cycles. This cycle is the one we studied last week. It's a diesel cycle. This is the ideal one again. The real one, as you saw, is banana shape, and this one is a closed cycle. Why is it a closed cycle? Because after all, we have, just like gas turbine, you know, we are, or the Brayton cycle, we have an air intake, and we have also an exhaust, so we interact with the atmosphere. But for this cycle, we make it behave, the diesel cycle make it behave like a closed system, which means there is, if we take the piston cylinder arrangement without the valves, neither inlet nor outlet, it behaves like a closed system. Just you deal only with the cylinders here. So it looks like a closed system, like the stove with a stove top with a lid, you see. So it's so there are two classes of thermodynamic cycle. They can be open cycle or closed cycles. Any of them are, a part of being open cycles or closed cycles. there are two classes of cycles, and what are they? They are the power cycles and the heat pump cycle. So we have two families here, two classes, independently from the open cycles or closed cycles. So what are they? This one is a familiar cycle. It's the diesel cycle again. And there are other power cycles. The diesel cycle is one, but you have the Otto cycle, as you know, it's the gasoline engine cycle. And the other cycle are, that time can be open, you know, they are open, but they are power cycles still. Like the Brayton cycle for gas turbine, the Rankine cycle for steam turbine, these are power cycles. So they are common. The commonality between those cycles is that they all use heat flow to obtain work. And they convert some the heat input into a mechanical work output. You see here the direction of the work, they produce work here. The arrow shows produce, and so you have the highest cycle temperature here. That's and the lowest cycle temperature. The condition and the cooling. So is the sum of efficiency of that cycle depends only on the absolute temperature, and remember what absolute temperature is. Minus 0 degrees Kelvin is minus 273 degrees Celsius, I remember well. So the sum of efficiency of a Carnot cycle depends only on the absolute temperature of the two reservoirs in which heat transfer takes place. So that's a hot temperature or reservoir, the low temperature reservoir. And here you can see the efficiency, eta, is expressed by this formula and simplifies into 1 minus TL, the lowest cycle temperature, divided by TH, the highest. So this Carnot cycle would be 1, but obviously, again, the reality is not, it's that, it's different, it's not, you're never reaching 1 or 100%, it's always under 1, but the closest to 1, the most efficient it is, the closest it is to the Carnot cycle. So now we're getting to closer to our subject, which are refrigerators and heat pump. And those are the second family of class of thermodynamic cycle. Remember, there were power cycles, and the second one is heat pump and refrigerator, the heat pump cycle. So now, how does the heat pump differs from the power cycle? The heat pump cycle differs from the power cycle. The natural tendency of heat is to go from high to low. So in order for that heat to go from low to high, we need to put some energy into it. So that's the direction of the arrow here showing energy input. Heat pump cycles transfer heat from low to high by using mechanical work as the input. And thermodynamic heat pump cycles, and we'll see it in a second. Yep. Thermodynamic heat pump cycles are the models for heat pumps and refrigerators. So this is their cycle here. We'll get back on that. The difference between the two, between the refrigerators and heat pumps, is that heat pumps are intended to keep a place warm, while refrigerators are designed to cool it, basically. So the most common refrigeration cycle, which is valid for heat pumps and refrigerators, which are basically the same, they are the same machines. The most common cycle for this is a vapor compressor cycle, which is using refrigerants like cool, otherwise freons, commonly that change phase. There are other gas refrigeration cycles like the reverse Brayton cycle, the same one as gas turbine but reversed, or the one that, for example, is the Hampson-Linde cycle. So everybody knows that what an air conditioner is, right? So air conditioners are heat exchange devices, and in other words, they convert warm air from inside space to chilled air when chilled air that they are sending back. So obviously somebody thought about reversing the process here, and heat pumps work the opposite way than the air conditioners or refrigeration systems or process. They turn cold air outside the house into warm air that they pump into it, basically. That's it. So heat pump comprises air handler inside the space, and an outdoor unit similar to an air conditioner, except it's called a heat pump to differentiate it. The heat pump draws in cold air, thermal energy from outside, and produces heat. So this way we can imagine that heat pumps and air conditioners as temperature transporters, moving temperature from one space to another. And we'll see that with those machine heat pumps and air conditioners, on a user standpoint, the heat conversion varies according to the season. So we'll be able to see that during the lab. It's interesting. So yeah, air conditioners are heat exchange devices. They convert warm air from inside space to chilled air. They send back. So the heat pumps have a lot of benefits. Since the 1970s, they have been more widely used because of the energy crisis. So everybody was starting to look at more energy efficient systems, but they are very efficient in raising the temperature of a confined space. So that means they use relatively less energy to do their job. In fact, an efficient heat pump, like we are capable of doing nowadays, may use about 4 times less electricity than a resistant heater. Obviously, it's more expensive, so even if you pay less electricity, you still have the payback issue for your equipment, so it may take a few years to pay back for it, but it's much more efficient. So a little bit more on the COP. The COP of a heat pump, or coefficient of performance. A refrigerator, let it be a refrigerator, air conditioning system, or heat pump, is a ratio of useful heating or cooling provided to work required. So higher COPs equates a lower operating cost. The higher it is, the best it is. But and the COP generally exceeds 1, especially in heat pumps, because instead of just converting work to heat, it pumps actual additional heat from a heat source to where the heat is required. So, but we can compare the COP roughly to compares to the heating capacity of a heat pump to the amount of electricity required to operate the heat pump in the heating mode. So it roughly compares that these factors, heating capacity of a heat pump to the amount of electricity required. So here are some formulas that we are going to use during the lab. And you see the COP is really defined by this formula, Q hot divided by, and that's for the heat pump, by Q hot minus Q cold. And the Carnot is this. And so, well, basically your CP is going to be 1, but we'll be explaining this a little bit further during the lab. So the coefficient of performance for the refrigeration is similar. You know, the COP is here. It was Q hot divided by the work. Here is Q cold divided by the work. And the Carnot reference here, ideal cycle, says temperature cold divided by temperature hot minus temperature cold. And again, these are absolute temperatures that you need to use here, kelvins. The COP is also more superior to 1. So, today's lab, the purpose of this lab is to perform a thermodynamic analysis of a marine heat pump, both heating and cooling operations. I think that heat pump comes from a yacht. It was designed to provide heat and AC to a yacht. So that heat pump utilizes, it works according to that principle, and it utilizes R22 refrigerant freon. During the heating operation, the R22 absorbs thermal energy here, the cool one, from a heat source, which is a tank, a 55 gallon isolated tank that you will see in the lab. The compressor then adds energy, work energy to the fluid, increasing its temperature and pressure. And then this heat produced is dissipated in a liquid-to-air heat exchanger using a fan and forced air to carry heat to the outside, to the room. Actually, it's a heating process. And then we can reverse it. So during the cooling operation, the flow of the R22 is reversed, and excuse me, and low temperature, low pressure, low temperature refrigerant that takes heat of the liquid to air heat exchange from that area. So, well, recognize the typical cycle here, refrigeration cycle. You compress, compressor, then you condense. Here, for a refrigerator, you know that heat is not used, it's just removed in the back of a fridge at home. You can feel touching it, it's hot, but it's air cooled, hence the need to keep some space, make it breathe and eliminate the heat in the back. So you will see the heat is eliminated, and so anyway it condenses. So from from gas here, hot gas, it cools it down and condenses it into a liquid refrigerant, and this is where you got the delta P, change of pressure, that for the cycle causes the freon to evaporate, and its evaporation removes heat or produces cold, as you wish. And so that's for a refrigerator. That's what is important. Obviously, that's the purpose of it. And now for when you deal with the when you deal with heat pump, that's the contrary you are doing here. You want the heat, so you just get that heat and send it into your room, so it heats it up, and the air outside is your heat source. It may feel cold, but as long as it's over 0 degree Kelvin, there is heat. At 0 degree Kelvin, there is no heat. So any degree above that is heat, even if it's minus 230 degrees or 73 degrees. So, well, in our heat pump here, the heat is taken from a drum full of tap water, and it's rejected in form of a heat. So in this process, the compressor is providing the way to go from the cold to the hot. So during the lab, we are going to monitor the temperature and mass flow rate of water and air to calculate the heat transfer rate for the heat pump using the information that we gather, the data, and the known electrical power consumption to the compressor. And we'll determine the heat pump's coefficient of performance COP, and also calculate the cost for using this unit in both configuration. It will be cooling or heating of refrigerator or heat pump. So on your handout, there is a very useful information, easy to read, but regarding terms you surely have heard about before, seen before. These are, for example, the energy efficiency rating, otherwise called EER, tons of refrigeration. What is it? You know, it's the capacity of a compressor. Sometimes people ask, what's the capacity of your compressor, HVAC compressor? Let's say 1 ton, 1.5 ton, 2 tons. So this is where you will find that useful information. So things to think about is which mode, heating, cooling, is more efficient. I think we provided some hints here, but you will have to demonstrate it. And does the temperature of the water make a difference? Here is a practical, convenient grouping all the formulas that you are going to use during the lab. And that concludes that discussion. Thank you very much, and see you in the lab. Bye.